Autoencoders. Autoencoders are neural networks used for unsupervised learning, specifically for dimensionality reduction and feature extraction. They work by encoding input data into a compressed latent representation and then reconstructing the original input from this representation. Autoencoders are useful for tasks like denoising, anomaly detection, and pre-training for other neural networks. So let's go ahead and implement a detailed line-by-line code for implementing an autoencoder in Python we'll use TensorFlow and Keras in this particular example. So first step is to import tensorflow.keras.model, import model from there. So I'm going to go ahead and import necessary libraries, which is this one. What this does is imports the model class from TensorFlow Keras models, allowing you to create and combine the input and output layers to define the entire autoencoder model. Next, from tensorflow.keras.layers, import input and dense. This imports the input and dense classes from TensorFlow Keras layers. Input is used to specify the input layers of the model where you define the shape of the input data. And dense is a fully connected neural network layer commonly used in feed-forward networks. Here it's used in both the encoder and decoder parts of the autoencoder. Next, import numpy as np. This imports the numpy library for array manipulation and numerical operations in Python. Let's go ahead and get the sample data, which is points in 5-dimensional space. So I'm going to say x equal to np array. Now this public array defines the feature data x as numpy array with data points in 5-dimensional space. Now each sublist represents a data point with 5 values which are features. Now for example, that first point 1, 2, 3, 4, 5 is a 1 point in 5D space. The shape of x is 6, 5, meaning there are 6 data points with 5 features each. Now let's go ahead and define the autoencoder model. You can just say input dim equal to x dot shape of 1. This sets the variable input dim to the number of features in the dataset x. Now when I say dim is dimensions. In this case it's 5. X dot shape of 1 returns the number of columns which are features in x, which will be the input dimension for the autoencoder. Next, I'm going to say encoding dimension equal to 2. So this specifies the encoding dimension, that is the number of dimensions to which we want to compress the input data. Here we set it to 2 to compress the 5-dimensional input into a 2-dimensional representation. Next, let's go ahead and do the encoder. Input layer equal to input shape equal to input dim, comma. This defines the input layer of the autoencoder with the shape of input dimension, where input dim is 5. This specifies that each input data points has 5 features. Next, encoded equal to dense, encoding dim, and activation equal to ReLU, input layer. This defines the encoder layer, which is dense, fully connected layer, with encoding dim neurons, 2 neurons in this case. The activation function used is ReLU, which is rectified linear unit, which introduces non-linearity to the model. The encoder reduces the input dimension from 5 to 2 by learning a compressed representation of the input data in this case. Next, I'm going to do the decoder. So decoded equal to dense input dim and activations equal to sigmoid encoded. So this defines the decoder layer, which is also a dense layer with input dim neurons, or 5 neurons in this case, to reconstruct the original input. The sigmoid activation function outputs values between 0 and 1, commonly used for reconstruction tasks. The decoder expands the compressed 2-dimensional encoding back to the original 5-dimensional space. Next, let's do the autoencoder model, where we'll say autoencoder equal to model input layers, comma, decoded. Now this combines the input and output layers to create the full autoencoder model. This model takes input layer as the input and decoded as the output, meaning it will take a 5D input, compress it to 2D in the encoder, and then reconstruct it back to a 5D in the decoder. Now finally, let's compile the model. Let's say autoencoder dot compile optimizer equal to Adam, loss equal to MSE. Now this compiles the autoencoder model specifying optimizer equal to Adam, which uses the Adam optimizer, an adaptive learning rate optimization algorithm commonly used for training deep learning models. And loss equal to MSE specifies mean square error MSE as the loss function, which calculates the average of squared differences between reconstructed and original input values. Lower loss indicates better reconstruction accuracy. Next, let's train the model. Once your autoencoder dot fit x comma x epochs equal to 100, batch size 2, and verbose 0. This trains the autoencoder model on the dataset x, where x is used as both the input and target. The model tries to reconstruct its own input in this case. Epochs equal to 100, which specifies that the model will iterate over the entire dataset 100 times. Batch size equal to 2, the model processes 2 samples at a time before updating its weights, which helps stabilize training. And verbose equal to 0 suppresses the output of the training progress for cleaner output. Next, let's get the encoded compressed representation by saying encoder equal to model input layer encoded. This defines an encoder model using only the encoding part of the original autoencoder. This model takes input layer as input and outputs encoded, allowing it to generate compressed representations. X compressed equal to encoder.predict. This what it does is it passes the input data X through the encoder model to obtain the compressed two-dimensional representation. The X compressed now contains the 2D representation of the original 5D input data. Next, let's go ahead and print the compressed representation. So this will print the compressed two-dimensional representation of the input data, allowing us to view the lower dimensional encoding learned by the autoencoder. Let's see how it looks like. Go here and say Python autoencoder py. It's going to run through the model, and here you go. We have the data here, the compressed representation. It shows the data here based on the data that we have sent here. So this kind of this code kind of trains an autoencoder to reduce 5 dimensionality data to 2-dimensional here, 2 dimensions here, which can then be used for tasks like visualization or feature extraction. The autoencoder learns to reconstruct the original data while compressing it into more compact 2-dimensional form in the middle layer. The encoder part of the model can be used separately to generate compressed representation of the new data. So if you have any problems or had any issues implementing this or have any questions for me, let me know and I'll get back to you.